Okay, looks like it's recording. Hopefully it doesn't trick me again. Tricking myself. Alright. Particular camera records about half an hour. So we're talking about superposition and space-time and superposition time, dual corpuscular time shared space, particle unitizing reality makers, which is the Big Bang was a singularity that we never left, creating us. So then let's see, I better take a read of what I'm doing here. Hey, there we go. See? I recorded something earlier and didn't, for some reason the camera stopped. I'm just going to check, make sure it's going. Yep, going strong. Alright. So, dualistic corpuscular time shared spaces, space-time, superposition time is two different corpuscular times within the dual corpuscular time shared space. This is a black hole. The black hole that we never left is the white hole of our existence. Every particle that's in the black hole, from its own point of view, is trapped and alone, falling to the center. Being at the center is anywhere within a special particle, and that particle is a space particle. The space particle is looked as one particle, all of space, and then space is divided because the gravity well goes down to a little, about 1 Planck width, and that is what the expected smallest reunitized particle is, 1 Planck length. And then if it's in a different black hole, then it would be proportionately different, but it would still be the same. So in other words, up to the event horizon, Einstein's theory of special relativity, general relativity, classical physics works up to the edge, and that event horizon is a point of separation. So inside of the singularity, you have to it's reunitized. So therefore, the only one we have access to is the one we're in. So we, with less amount of gravity, less mass, would change the dual corpuscular time shared space. So as you can see, you can imagine that within there you have a space. That space particle is divided up by Planck lengths because imagining it's conceptual that the gravity well is held open by the unitized particles, but also the space particle, those positions are also valid, which means those are also sliced and diced up into 1 Planck length, and the whole of all space is sliced up like that. And those areas are part of the core, and that core is like a matrix, but not like the Matrix the movie, but like a core moving, but not from our own perspective. It is relativity. So every particle is falling to the center. From its own point of view, it is in the center. And if a particle is moving through space, the particle believes it's moving through space, but from the space's point of view, space is wrapping around the particle rather than the particle moving through space, because there's no edge to this particle of space. It's just it wraps around itself. So there's no wall, there's no height, there's no width. You can't measure it that way. And the quantity of how it's going to be reunitized will probably depend on the amount of mass that's in it. So therefore, and as far as this thing about God, it's so annoying when I listen to this. Because I've been getting annoyed because I know something else, right? So it's tough to know without sharing because it's getting frustrating. So in other words, the moment of inertia, you have in light, you have electromagnetic, and in all particles you're going to have something similar. And and if you look at a planetoid, like say like Saturn, you've got the rings around the equator. And so in my model, I've chosen to make that a sample of what the potential particles would be, and the virtual particles would be the ones that create, like, say, around the planetoid, like on Earth, our magnetic field. So you've got energy that's magnetic in one direction, and the other direction you've got potential matter. And so the potential particle runs perpendicular to the virtual particle, and when they coincide, cooperate within their frame of references, a particle is created. If that's a permanent cooperation, then it's a permanent particle, at least until something interrupts that process. So then now you can see that the mass is a trajectory in space-time and in superposition time. Those trajectories are perpendicular to each other. So when you push something that is a particle here, it interrupts a trajectory. And that interruption of trajectory coincides with the black hole's ability to hold that thing in place. And once you move it, then that is satisfied, and it readjusts, the trajectories readjust themselves. So, if you telling you how the moment of inertia works, that's how it works. The trajectory within the energies that create the the moment of inertia are a trajectory. And when you push on something that resists, you're interrupting those trajectories that have to readjust. And once they readjust, they're in the middle again. Every point on a particular object is in the middle. The argument that's won is between two particles. So within mass, every point in that mass is the center. I'm sorry. Within the space particle, every point within the space particle is the center. So every part of space, wherever you are, is always going to look the same, and that includes the optical illusion of the acceleration. When you get further out from the middle, from my point of view, if I look way out, then logically the only way that could be out that far is if it was being accelerated away from the center. And so it's a mirage effect. It's not all of it. There are accelerations, don't get me wrong, I'm not trying to, but there is another particle physicist out there who is in agreement with me on this, and he's been telling everybody, and he apparently can't make any headway due to various reasons. Okay, so if none of that interests you, you probably aren't going to be interested in what follows. So, I think I'm going to read, so I find something to talk about here. Explaining spooky action at a distance. You might say, well, you got a particle in the middle, and it says it's in the middle, it's all alone, it's falling to the center of the black hole. So, yeah, from its point of view, I wanted to cover a couple things. One is that when it falls in, it believes it's doing this trajectories around the center of the black hole, and the center of the black hole is a attractor. And that attractor, the particle's going around and around and around. Let's just do an imaginary trajectory, not so random, yeah, like that. And it's coasting around like that, and then and it's going, also obviously fast. So now that's the point of view of the particle. It doesn't really notice it's trapped by the black hole. It just is going about its own business. And it is reunitized. Its diameter has changed. So now let's look at it from the perspective of the space particle. That means all of space looks at that particle down the middle of it, and it says it's trapped perfectly still. But the space is actually moving around the particle, giving the appearance the particle thinks it's moving around, when really it's just space moving around the particle. Both of these are just extended forms of special relativity, or general relativity. Anyway, it's a relativistic point of view. A relative point of view. Yeah, extended form of relativity. So, each particle is on its own frame of reference. So if you take two engaged, I tried this earlier, I ran out of time. It really irritated me because I've been trying to do this several times. It looks like I got plenty of time. The camera's going, batteries are charged. Let me get this out there. Okay, so now we've got that famous entanglement. We bring two particles together. We energize them. Okay, this is not literal. This is conceptual. You energize the particles, and they're energized. And now they're doing this thing, right? And we bring them apart. And so now imagine in your mind that you have your horizontal energies and your perpendicular vertical energies, and those trajectories, because that's what we're talking about here. These two are entangled because of the trajectories. So when the trajectories are entangled, it's rather obvious that when you take one of these out of the picture, you've measured this one, now this trajectory is just stuck going in an up. From your point of view, from your frame of reference, you're only going to get it on the up now. But if the other one was there, and then we pulled it out of we measured it, it was up, then this one's always going to be on the down trajectory now, or this way if you want. Anyway, so now that's when that measurement occurs, it's always going to be on the down trajectory, and I know I'm saying it in a way that's very conceptual, so you get what I'm saying. So you can move these frames of reference as far as you want apart. These things are nothing but a trajectory between as far as the singularity is concerned, any point within the singularity space is just the center. It doesn't care. So you gain degrees of freedom within this space particle. You can go anywhere in there and still be trapped by the singularity. It's I call it the white hole of our existence. A little different definition of white hole. But what else would it be? It would be like the correct interpretation of what white hole really means. And the fact is that everything that pushes out in our reality, all these particles that they don't know why they're binding, is because they're binding because they don't have anywhere else to go. They're trapped by the singularity. When you jump on this planet, you're being pulled down to the center of this singularity. If you're on the moon and you're jumping, and you're being pulled down to the center, you're being pulled down to the center of the singularity. Wherever you are in the matrix of the space particle, in the core of this space particle, you're either independently in the middle with no gravity floating in space. One particle doesn't matter, one piece of space doesn't matter, nothing in it except for potential particle and virtual particle that is connected. We'll get into that later. We need some diagrams for that kind of thing. So anyway, fits very well with these things. It's amazing. This is my model of quantum gravity, and if you take let me see. Well, let me just read on a little bit further here. Gravity is a particle falling to the center of the black hole. Gravity is all particles falling to the center of the black hole. Gravity is averaged to the outside of the mass. Oh, so to the Planck length, every particle that's trapped within the black hole, including just a space particle, or this all space divided up into these Planck widths, is why you don't have shearing force gravity everywhere, is because it cancels out all the gravity. Beautiful, huh? And so the canceled gravity, the only leakage there is in substances. And in substances, you have a very small amount of leakage at the Planck scale, at the Planck length, and that leakage causes what we call gravity. So, and then also within our space, you can create a singularity. And that singularity is a new dual corpuscular time-space particle reunitizing reality maker. And inside there would be some form of a reality. But that reality would also follow the rules of light speed proportionately to what ours is here, except that it would be a different, it would be relatively different. That is exactly what this is all about. So pushing or turning a trapped particle is inertia. It changes the trajectory. The same kind of force lifts like a superconductor. When it goes into superconduction, it starts to be easier for the current, the magnetic field to pass through, and the magnetic field actually lifts that superconductor off that little track, or off that little ground, that, you know, whatever you have for a superconducting example. Any direction of motion turns a particle or pushes a particle in any particular direction gives us inertia. Any push from a particle against a particle B against A, or A against B in regard to the center, and thus you have a moment of inertia. The singularity is a combined effort of all particles in the singularity to hold that particle in the center. Since there is not much mass per one particle, this is a proportionate force holding that particle until it moves in space. Once it moves, then the inertia is satisfied and the trajectories adjust. Inertia is the black hole on a single hold on a single particle. A single particle being pushed in a straight line through space is a curve in relation to the center of the singularity. The moment of inertia is the resistance of the singularity to release that particle. Let's see what time I've got left. Oh. Okay, about 10 minutes. So, an adjustment is then satisfied, and the resistance is gone unless another force is exerted. The cumulative gravitational grav is equal to the total gravitational mass exerted on that particle. If the particle is massive enough, then it phases out of this time in a new dual corpuscular time-shared space. The lines perpendicular to the motion of a particle pushed in any direction is crossing the lines that are curved. A particle at the edge will be redshifted. A particle in the center will be a particle in the center is just in the center, but anything in relation to that particle on the edge from the particle that's in the center's point of view, if it's far enough to the edge, it'll be redshifted. And if you're on that particle, the other one would appear to be redshifted. Any particle traveling away from the center, say like a photon traveling towards the edge of space, will be maximally offset from the center. If it could be massive enough, it would become a black hole or a stationary particle massive enough would realign space-time already proven, and a black hole of, let's see, an extreme of the same thing. There are open, this is just part of my model, I guess. I think that within this model there are what I call open door black holes and closed door black holes. This explains lensing effect. What I'm saying there is that there are black holes that will tend to whip things around rather than let them in, because they're so fast. They just won't let anything get in them. And then there's others that are open to where stuff can go past the event horizon. This also can help explain certain kinds of lensing effects. I should say this could help explain that. There may be null space. What I mean by null space, there might be outside of space-time, there might be the null, well, it had to all come from somewhere. The black holes hold on a single particle as its moment of adjustment in the space particles flow around that single particle. The single particle is trapped in the center of the black hole. From the single particle's point of view, it is alone in the center of the black hole, and away from its point of view, it is moving normally around the attractor, but from the black hole's point of view, it is moving around the particle to keep it trapped in the center. Such is an extreme case of dualistic corpuscular time within a reunitized supertime space-time relativistic relationship between the energy and potential particle. The black hole is where reality starts. You can look at it as a Big Bang or as an implosion or something. I prefer to look at it as a Big Bang that was there for a very long time, but nonetheless the formation is best explained by the black hole being a time-setting reality maker. The existence of a black hole logically explains more than the questions it makes. Now, this is the mind-blowing part. Basically, is where it is a singularity, but the singularity is not infinitely small. It is in one sense, but in another sense, it reunitizes itself. Think of it like a spring. Every piece of matter is a spring of its own existence. It is already in an equilibrium with this reality. Within this time structure, it's settled into its own equilibrium. So when it passes through the black hole, it has to redo that. That's why we don't see it. That's why it vanishes. Is because it's reunitized and it's not compatible with this time-shared space. Even superposition is only semi-compatible with this time-shared space. Frames, imagine it like frames. You've got, say, 2 frames here, 4 frames here, and if you have a partial match, that's a partial match because the frame is going frame between. It's still going to be affecting these frames, but it's not going to be on them. If they're on them, if the frame of references are combined or entangled, then you have a persistent match between frames of reference. More of that later. Let's see how much time we got left here. Time tends to go by pretty fast. About 5 minutes. So, let's see if I can find my place here. The black hole is where reality starts. You can look at it like a Big Bang. Oh. The existence of a black hole logically explains more than the questions it makes. And the existence of the type of black hole that I'm talking about, which is our reality, makes more sense. It answers a vast amount of questions. I call this process of your science, whatever it may be, and this, like strings. You know, somebody might say, well, you can just take string theory and throw it out. Well, those strings look an awful lot like trajectories to me. And in mine, you have all these trajectories that are very tiny. And those trajectories, if you took an accumulator here and here, and you had a shared loop between the two, and you're pulling these apart, and if it's still exchanging between the two, you could have a loop that's being stretched kind of like a rubber band, and all it is nothing more than a trajectory of a particle. It has a certain kind of rule where when you pull on it, it's going to keep in line with these two particles, and it's almost like it's stitched. So, you know, I'm not saying yay or nay on this particularly. What I'm saying is that the process of determining how you know, I believe that trajectories are the answer. You know, like a trajectory going who knows how fast, you know, light speed. But in superposition, it's obviously within that time shared space, it is light speed. It's no rule has been broken, but it is also, from our point of view, with what they call the wave function, it's fuzzy. It's not fully in alignment. They're out of phase. So that's what helps to make our reality. So the center particle has a diameter of 0. That's what I was getting at. In the black hole, the particle might have a diameter of 0, but the particle has a diameter at the same time, because the reunitization of the particle is what recreates the event of the Big Bang. Source of its singularity is debatable. Okay, so like if I'm saying like, where did our black hole come from? It could have came from another time shared space just like ours. It is it a tiny closed door singularity or something that uses the black hole singularity? So now I'm kind of getting into the particle that fell into the singularity. Is it a singularity of its own? Or is it part of this singularity that makes the singularity fight back? That doesn't even make sense. I would say it has to be a singularity. And I'm not talking about an atom. I'm talking about a Planck length. And from the point of view of the space particle, if you do have a small particle that's reunitized, you can't say it can't exist, because now it's reunitized. That reunitized space, if that is a particle, if we call a black hole a particle, and in this case, there may be some special feature in regards to this, but nonetheless we know that particles exist. We know that particles go into black holes. If the source of a particle is a black hole of its own, you take a space particle, take a tiny one and a big one, and if you go inside those, since in space, I mean in these two different spaces, even though there's a size difference from the way we're looking at it, we know about that size difference, but once you're inside of it and you have no frame of reference, you cannot tell the difference. There would be no way for you to measure it. They would both appear to be identical. So that's why I'm saying that microsingularities can exist, and not for this billionth of a second or whatever. They can exist for incredible long periods of time, because it would be an equilibrium setup. It's like decay rates on matter. You know, you've got some that are stable, some that are unstable. So I have kind of leaned towards the idea that the stability of a particle is a equilibrium of a, like if you imagine a singularity that's made from, say, like there's as least amount of space inside of it as possible. Say it's crammed full of iron.